Right, in this lecture, I'm going to do the first round of instruction on all things correlations. It might seem like a deceptively simple topic, but there's actually a little bit more that goes into computing, understanding correlations than you might think from the get-go, so that's why it's going to be split up into two installments. So to begin, correlation is basically going to be a way to describe the strength of the relationship between two distinct variables. I know for some project groups, I sort of got on you to make sure you had separately defined variables and you had separate scales to assess each one distinctly. That's because key for doing a correlation is to describe the relationship between two distinct variables, and as such, the two variables do need to be discrete and distinctly defined. Additionally, correlation is going to capture certain quality of the relationship between two variables. Basically, variables can be related on a spectrum from non-existent to weak to very strong, and the direction of that relationship can either be positive or negative, and your correlational analysis will be able to tell you all of that information. It's additionally an approach for research design. So I'm going to touch on both the design aspect of correlation as well as the computation over the course of these two lectures. So to give you an example of how correlational research looks and might work, using an example that got some mainstream attention a few years ago, was this research done that looked at the relationship between Nobel Prizes won in any country and the amount of milk or dairy consumed in that country. So basically, do countries who consume more dairy also tend to win more Nobel Prizes? Now, this first screenshot from just the Daily Mail, which is obviously a not very reputable outlet, you see titles like "Drink More Milk, You Could Win a Nobel Prize." Nations that consume more of the white stuff have more laureates. So that was the basic conclusion from the correlational research. Countries that consumed more dairy did tend to have higher amounts of Nobel Prizes. Here's where you want to make sure that you're being critical and you're thinking critically about what correlational research can actually tell you. This headline's a bit misleading, right? Drink more milk, you could win a Nobel Prize. Obviously, the relationship between dairy consumption and Nobel Prizes is there, but it seems a bit of a stretch to me to conclude on the strength of that research that the milk itself caused the Nobel Prizes to be won. As this headline sort of insinuates by saying, drink more milk, you could win a Nobel Prize, they're speaking about a possible causation type relationship when you really can't do that. Now, even a more reputable outlet like the BBC falls into the same trap, saying something like, does chocolate make you clever? Now, they're hedging a little bit by forming it in the phrase of a question, but it's still inherently misleading. This research was correlational. They found that more dairy was associated with more Nobel Prizes. To act like it then is the logical conclusion to say that the dairy makes you smarter, there's so many flaws in that statement. You can't make that leap. There's so many explanations for this relationship besides the dairy causing you to win more Nobel Prizes, or as the BBC said, make you smarter. If you look here at the country by country breakdown, what you see is that there's a possible alternative explanation lurking that might help us understand this correlation. You see the countries that consume the most dairy and win the most Nobel Prizes. You're seeing Western European countries like Sweden, the home of the Nobel Prize. I'm not surprised that there's a lot of Nobel laureates there. Other countries like Switzerland and Denmark, these are very wealthy countries that have a lot of access to great universalized education. And all of those, in my opinion, sound like a much more logical explanation for why these countries win more Nobel Prizes. So maybe the fact that these countries have more money and are able to consume luxury products like chocolate, that is also coincidentally partially why they win more Nobel Prizes. So any number of other explanations make more sense. Cultural factors, educational factors. The idea that this correlation by itself can speak to a causal relationship As always, correlation doesn't equal causation, so you want to have a more critical eye when you're seeing sort of overblown or sensational research like this. And so throughout these lectures, we're just going to talk all things correlation. So when you are confronted with correlational research and analysis, you know how to properly interpret it. So like I said, key to defining a correlational research question, which ultimately leads to your ability to do a correlational analysis, is going to be a question driven by trying to find an association between two distinct variables. I'm going to use the X and Y shorthand to talk about the two variables that are always at play when you're talking a correlational research question. So for example, does greater attractiveness predict greater likability? You've got your variable X, you've got the association term linking them, and then you've got your second variable Y. Does the accuracy of performance decrease as speed of response increases? In this case, again, there's two distinct variables, and you're predicting a association between them. In the case of these two statements, predict greater or decrease as, are indicating directionality. You can definitely have a correlational research question that is non-directional in nature by having your association word be something like affect, or is associated with, or is correlated with, where you don't have this language indicating that you predict a positive or a negative correlation. That's completely fine. Again, when you're formulating your correlational research questions and claims, make sure not to go to that next logical step of stating causality, because again, on the strength of correlational research, you can't claim a causal relationship between your variables. You could certainly speculate which variable you think is more likely to cause changes to the other, but you can't indicate that correlational research gives you direct evidence towards causal direction between relationships. You might be thinking, if there's this inherent limitation to correlational research where you can't make the stronger causal claim, why is it so commonly done? And there's lots of reasons why you might want to do correlational research as opposed to more difficult experimental paradigms to demonstrate causality. One that I don't even list here is that it's easier. It's a great way to start. It's an easy way to get a handle on which variables are associated. And the fact that it's logistically easier to do than an experiment, it just makes it a really great way to start. But another important reason is that sometimes it's ethically dubious or even impossible to do an experimental study where you, the researcher, are manipulating your variables. So if you're interested in the relationship between variables that you can't meaningfully manipulate, correlational research is going to be a really useful way to try and pin down which variables are associated and in which way. So one example of variables that we know are related, but it might be ethically impossible to actually manipulate them. There's a lot of very compelling research indicating that smoking cigarettes leads to lung cancer. Now, it would be ethically problematic to manipulate cigarette smoking. That is to say, you can't place someone into a condition where you're telling them to begin smoking cigarettes. At this point, we have too much knowledge about just what cigarettes do to your lungs and what they do to your body that we can't do that. That doesn't mean that we can't conclude that cigarette smoke causes lung cancer. The reason we can do this is A, there's a mountain of correlational research, and B, we know that cigarette smoking comes first in time. People smoke cigarettes throughout their life, lung cancer happens later. You don't see it being the case ever that somebody gets lung cancer and it drives them to begin smoking. That just doesn't make sense in terms of how these variables occur in time, or there's no logical explanation where that would make sense. So even though this research linking cigarette smoking to lung cancer is correlational, that doesn't mean that we don't have enough strong evidence to conclude that cigarette smoking does indeed cause lung cancer to occur. Now, there are limitations with correlation besides the obvious that I'm going to get into. One is that your correlational research and analysis is going to be sensitive to what we call outliers or extreme cases in your data. They are sensitive to what we call a restriction of range. So if you don't have the full breadth or spectrum of diversity on either of your variables, it's going to limit the extent to which you can accurately capture the correlation. Your classic correlational analysis that we're going to use with a Pearson's R only works for describing the association between linear relationships, and not all variables are going to be related in what we call a linear fashion. And then, this being the obvious, correlation obviously does not imply causation. So be careful with your language when you're describing correlational research, and be wary whenever you see correlational research reported that does imply causality. But for those top three, I'm going to go through that list and describe a little bit more in detail what all of these mean and what they look like. So when I say correlational research is sensitive to outliers, I'm going to show you a bunch of scatter plots, which, as we covered last month or a few weeks ago, scatter plots are a great way to visually inspect a correlation, since it depicts a series of data points whereby their placement along the x-axis tells you where they fall on variable x, and their placement along the y-axis tells you where they fall on variable y. So the placement of the dot tells you about the association between variables x and y. So here's an example where you would see data that has an outlier that greatly impacts the strength of the correlation. This particular scatter plot here depicts a series of data points down here that look pretty cloud-like in nature, and if you were just looking at those dots, excluding that extreme one up there to the right, would probably not be a particularly strong correlation. But that data point all the way up here in the top right corner greatly skews the correlational value that you end up computing after you run your numbers. That single outlier, right, a very extreme score that's sort of out of step with the rest of the data points, by itself can impact the numerical outcome that you obtain. So the question becomes, does this data point genuinely belong in this data set, or was it a mistake with the data set? Is there some reason that that participant should be excluded? So if you're doing correlational analysis, you do definitely need to think about the presence of outliers in your data set, because it can impact your analysis. An outlier can also have the effect of causing your correlational outcome to be weaker. So in this case, you see two scatter plots whereby removing that one outlier actually increases the strength of the correlation, because the rest of the data points were telling the story of a strong correlation, and it was just one outlier that sort of wasn't falling along the same lines as everyone else. So again, the question is to think critically about whether or not the outlier belongs there, or if there was a problem with that particular data point that would warrant their exclusion from analysis, because the presence or absence of a single data point can and will impact your correlational analysis. Restriction of range, what this means is that if your sample is limited in terms of its range or diversity on one or both of the variables, it might be harder to get results. That is to say, it might be harder to get an accurate and fully fleshed out vision of the nature of your correlation. So the question becomes, how do I make sure that I have sufficient representation on both of my variables of interest? So to do this, you just need to think to yourself conceptually, what's the appropriate range for any one of my variables? So to give you an example of what this might look like, here's two scatter plots that depict the correlation between grade school level and knowledge of geography. If you look at the scatter plot on the left, that cloud of dots definitely does not tell the story of a particular strong relationship between grade level and knowledge of geography. Seems like it would be a pretty small correlation if we analyzed that data. It might still be positive, but we might conclude that there's no real relationship between grade level and geography. Now, when I say restriction of range, the idea is that this school grade level being truncated just to include grades 1 through 3 is too much of a restricted range to accurately capture the breadth of grade school levels. A more appropriate and non-restricted representation of this variable would be to capture all of the grade levels 1 through 12. If you were to have the full range and diversity that exists on this grade level variable, you then see a much clearer picture emerge of that correlation. You can see that there is in fact a strong positive correlation. It's just that by truncating this variable to be insufficient to capture that range, you do not get an accurate picture of just how strongly those variables are correlated. So then this point about linear relationships. So this gets at a function of relationships between variables whereby different types of lines might be differentially useful for describing different kinds of relationships between variables. This might be a little bit tough to wrap your head around in the abstract, so I'm going to show you different kinds of examples. But the first example of a type of relationship between variables is what we call a linear relationship. This is when the relationship between the variables, as visualized on the scatter plot, if there was a single line that would best fit all of those data points such that the line minimized the distance from all the data points to that line, would be just a straight line like this. So if, for example, you were depicting the relationship between ages of partners in a romantic relationship, you see those variables, they form a pretty distinct visible straight line. So the best single line that could be slapped sort of through the middle of this cloud of dots that would sort of best sum them up would be a single straight line through there. That's what we mean by a linear relationship. If you can kind of look at the dots and it sort of looks like it would best be described by a straight line, if you were to draw a line right through the middle of those dots, that's what we call a linear relationship. Variables that, when you depict them like this, can be best summarized by a straight line. You might be thinking to yourself, okay, well, are all variables related in a linear fashion? No, that's the problem. Many pairs of variables are best described as related in a linear fashion, even if you don't have that perfect shape that the dots tell, as in the last slide, where you can really visibly see that straight line. Even if it's something like this, where the dots are maybe a little bit more cloud-like, still the idea is a single straight line slapped through those data points still does the best job possible of summarizing those data points using a single line. So the fact that variables are related in a linear fashion doesn't necessarily have anything to do with the variables being strongly related or even that they're related at all. Just that the data points can best be summarized by a straight best fit line. Now, like I said, there's plenty of relationships between variables that are related that are not best described by a straight line. So for example, if you have any pair of variables whereby an increase in your first variable is associated with both increases and decreases in the second variable, you're going to end up with a nonlinear shape. A famous example of this, as depicted by the Yerkes-Dodson law from cognitive psychology, is a curvilinear relationship between your variables. So the Yerkes-Dodson law, if you're not familiar with cognitive psychology, is that the relationship between arousal or agitation, like physiological arousal, and your performance on a task is related in a way that's best summarized by this curved straight line. What this shape basically tells us is that there's a sweet spot whereby your arousal level is enough that you're not falling asleep, but not too high where you're extremely jumpy and agitated, and that's where you see optimal performance on cognitive tasks. So a linear relationship would necessarily be one whereby you would see that relationship with X associated with either increase or decrease in Y, not both, along different points along the X-axis. For this relationship between variables, you see that as we go up the x-axis, you see y rise, hit that sweet spot, and then start to decline. If you were to try and draw a straight line through data points that had this curvilinear shape, you would end up drawing just a straight line here, because that would be the straight line that sort of best describes dots that take on this curvilinear shape. The problem with trying to slap a straight line on variables that are related like this is that you would be left with the assumption that the variables are unrelated. If you have variables that are related in a non-linear fashion, You can do a correlational analysis. It's just that that analysis would tell you that the variables are unrelated. Variables are able to be related in a more complicated way than just a single straight line. So that's something to keep in mind if you ever find variables are unrelated, but you think there's reason to speculate that they might just be related in a more complicated fashion. If you ever have that feeling, it's worth asking yourself whether or not a nonlinear shape might be best for describing the relationship between your variables. So there's lots of different examples of nonlinear relationships between variables, right? Something like the law of diminishing returns, whereby investing more time, energy, and money into a business only gets you up to a certain point before you're just wasting money. The law of diminishing returns definitely is that there's a relationship between your variables, but again, you see a sweet spot in the middle, and then you see these curves on both sides. Another example of a nonlinear relationship, you might see variables that are very, very strongly correlated up to a point, and then you see that line taper off such that once you get up to a certain point, that relationship becomes very, very weak. So if I were to slap a straight line onto data that looked like this, I would probably assume that the variables were moderately related, when in fact the relationship between the variables is just more complicated than that. If you have a very, very strong relationship between variables up to a certain point and a very weak one beyond that, your single correlational analysis is going to miss all that information. And then we have what are called S-curves, which on the other hand, as opposed to this graphic here, shows very, very weak relationship between the variables at both high and low levels, and only a strong relationship here in the middle. For something that looks like this, for an S-curve, you could still definitely do a correlational analysis, and likely you'd find a relationship. But again, if you do have variables that are more accurately described as being this S shape, just doing your correlational analysis is going to miss the nature of this correlation. It's going to be slightly inaccurate. So now I'm going to talk about the different quality that correlational relationships can take on. So the type of correlational relationships we see, one is what we call a positive correlation. This is when as levels of variable x increase, so too do levels of variable y. So anytime you're speculating that the two variables sort of travel together such that as levels of one rise, so too do the other, and as levels of one decrease, so too do levels of the other. What you would see on your scatter plot would be data points that increase or that slope upwards as you move from left to right. So you see the shape of that line slant upwards as you move from left to right. That tells you that as levels of this x variable rise, so too do levels of that y variable. So people who smoke more cigarettes tend to have more lung cancer. People who smoke less cigarettes tend to have less lung cancer. And you can very easily tell that this is a positive relationship because, again, that line is sloping upwards from left to right. A negative relationship, on the other hand, a negative relationship is the presence of a correlation. So don't get confused and think that a negative relationship means absence of a relationship. A negative correlation is a correlation, it's just that it is in the opposite direction. So negative correlation is whereas levels of your first variable increase, levels of the second variable decrease. Okay? So this would be something like the relationship between exercise and heart disease, right? As you exercise more, you see health outcomes diminish. More exercise, less heart disease. Or like this scatter plot that depicts the relationship between hours of video game playing and GPA. The difference in visually assessing this scatter plot as opposed to the one on the previous slide is that this best fit line is sloping downwards as you move from left to right, indicating that as level of video games go up, you see GPA being lower. And as video games go down, you see GPA being higher. Hey, again, this is a negative relationship. There is a correlation there. It's just that it's in the opposite direction of the ones that we saw in the previous slide. Another facet of your correlational analysis beyond describing the direction is going to be to quantify and capture the strength of the relationship. So any correlational analysis is going to describe the relationship between variables by where they fall along a spectrum. The spectrum of possible correlational analyses is from perfect to imperfect to zero. Okay? There can only be correlations within this range, from zero to perfect. Now, if you have an imperfect correlation, that correlation is going to fall somewhere between this spectrum of a zero correlation to a perfect correlation. So a perfect correlation is where all of the data points in your scatter plot fall exactly along that straight best fit line. What this means is that you know with perfect predictive accuracy where somebody falls on variable y if you know their value of variable x. Now, in real terms, we are never looking for a perfect linear relationship between our variables. That's just not feasible unless you're correlating a variable with itself. We are never looking for a perfect relationship. It's just that we know that our variables are going to fall somewhere within that spectrum, and we just want to know where. How close to perfection is our correlation? So your imperfect relationship, on the other hand, is going to be where not all of the data points fall along that best fit line. So here's a visual to show you all of the ways that you can fall along that spectrum. So you can have a perfect correlation that is either perfectly positive or perfectly negative. In both of these cases, indicated here, you have a perfect correlation because all of the dots in the scatter plot fall along that best fit line. So you can have that perfection be a positive correlation or be negative. That means that your correlation can range from perfectly negative, which would be quantified as a -1, to perfectly positive, quantified as a +1. Like I said, you can really only fall along the spectrum from 0 to this or 0 to this. So in effect, your R value and your correlation will necessarily fall within the range of -1 to +1 because you inherently will need to land somewhere in between here. And when I say somewhere in between here, in between those two, these are all the other examples of what you might see. You might see variables that are positively related. They could be quite strongly positively related, as here you can see that those data points definitely are quite coherently clinging to that best fit line. That appears to be a quite strong relationship, not perfect, but we're not seeking perfection. It might be a bit weaker. You can see more of a sort of a diffused cloud-like shape, but still, if you were to crunch the numbers on the correlation between these two variables based on this scatter plot, you would still see a positive correlation. You might see a negative correlation, where that cloud of dots is again sloping downwards from left to right. And then, lastly, you might find that you have what's called a zero correlation. So this would be when the slope of this best fit line is perfectly horizontal and the dots around it are just basically completely cloud-like and amorphous, basically almost circular. It's still a straight line that best describes this data point, or this set of data points. It's just that that line is perfectly horizontal. This would indicate what we call a zero correlation. So when we're doing our correlational analysis, the idea is that some relationships are going to be closer to perfect than others. And this is going to relate to what we call the strength of the correlation. So if you've ever heard that there's a strong correlation between two variables, this is really just capturing that level of perfection with which your variables are related. How close to that best fit line are all your data points? Your correlation is just going to be a quantification of this strength. So how do we do that? How do we actually quantify the strength of our correlation? To do that, we're just going to calculate a Pearson's R. So I'm going to pause this video so you can take a break before getting into the Pearson's R, and I'll pick back up with how you actually run that computation.